Last time we dealt with orthogonal projections. So if we had a subspace W that had its orthogonal basis and orthogonal bases, what we could do was take some vector that didn't live in that subspace and project it down so that its shadow could be represented in terms of that orthogonal basis. So this was what was called the orthogonal projection of the vector x onto that subspace W. The weights of those basis vectors were really easy to find because of orthogonality. So these weights had a formula. They're called Fourier coefficients. And once you have that, it's very easy to work with. The real question is, all of those things were predicated on having an orthogonal basis. So what if I don't have an orthogonal basis for my subspace, right? How can I find one? Because if I don't have one, then I can't really do all of this other stuff. Well, the answer to all of this is we're going to use projections. So there's a process that you can use projections and come up with an orthogonal basis. So this is something that's going to be called the Gram-Schmidt process. And it could also be referred to as an algorithm because it's going to be a set of steps that you can follow to create an orthogonal basis. So it's a set of steps, that create an orthogonal basis. And what you need is a basis to start with. And we're going to use projections to do it. So we're going to start simple. Here's a very simple way of thinking of it in R2. And if we take a look at this, let's just kind of represent it by a plane like this. If we have a basis for R2, let's call it V1 and V2. Now, those vectors could look like a lot of different things. All that's important is when you're in R2 is that those vectors are not multiples of each other. Now, this is certainly a basis for R2. What we're going to do is we're going to create an orthogonal basis using a projection. So remember that if you were to take a flashlight and shine it down onto the direction of V1, you would get a shadow. And that shadow right there, this thing V2 hat, would be the projection of V2 onto, and we're going to think of it like this. It's going to be the subspace spanned by V1. So this thing right here, we'll call this the span of V1. We can call it W. So we are going to project V2 onto W, onto that line. Now we know that there's a nice little formula for it. It's just going to be V2 dotted with V1 over V1 dotted with itself. And then we'll multiply that by V1. Now, the key idea here is that at the same time, we are able to break any vector into orthogonal components. So right there, this second portion, V2 with the perpendicular symbol, that is the one that we are interested in. So we now know that V2 with the perpendicular symbol, V2 perp, just by using simple vector addition, is going to be V2 minus this thing, V2 hat. And that vector right there, this one is orthogonal to that subspace W. And if it's orthogonal to W, then it's also orthogonal to that vector V1. And this is how the process is going to work. We are going to choose the following. So we are going to define like this. The orthogonal basis is going to be denoted in this case by W1 and W2. And we're going to choose any one of the vectors as the first vector in the orthogonal basis. So we'll say that W1 is V1. And it can be any one from your original basis. It doesn't really matter. Just because of my picture, I'm picking that one to be V1. And once I've got that, then what I'm going to do is I'm going to project V2 onto the subspace spanned by V1. And when I do that, I will get v2 with a hat. And then I'm going to let the second orthogonal basis vector be the perpendicular component, v2 with the perp. That's going to be v2 minus v2 hat. That's going to be v2 subtract v2 dotted with v1. But in our language, v1 is the first orthogonal vector. And we are now done. That was my set of steps. I now have an orthogonal basis W1, W2. Easy peasy, right? All I had to do was use some basic projections, and I am finished. Now, here's a really important point. The original basis was some vectors, we're going to call it v1 and v2. Their span were made up R2 in this particular case. Now, if I were to talk about W1 and W2, the new basis that I made, I want to talk about the span of those two new vectors. By definition, span means every vector that you can form by taking this linear combination. Well, this is the same. Remember, W1 was the same as V1, and W2 was just some linear combination of the original two vectors. So I'm just going to call it K. And you can see that from above up here, right? It's just some multiple of K, of that V1. So at the end of the day, when you put this all together, you're going to get some bunch of V1s and some bunch of V2s. And if you take any linear combination of W1 and W2, it's just going to end up being some linear combination of V1 and V2. And the point of all of this is that the span of W1 and W2 is exactly the same as the span of V1 and V2. You're not changing this object that they span. All you're changing is the basis or the language that you're using to describe everything here. So one set of basis vectors looks like this, the other one looks like this, but regardless, they will all create the same space. And that's what's really nice about this process. Regardless of which vectors I choose, they will always span the same geometric object. So as an example, you can take a look at a space here in R2. We'll take the coordinate axes and we'll go like this, 1, 2. Let's say we have V1 is the vector 0, 2, and we'll say that V2 is the vector 1, 1. So 0, 2 is this first vector up here, and the second one here. So there's V1, there's V2. These are a basis for R2. So V1 and V2 are a basis for R2. They are not independent, or sorry, they are not multiples. They are independent, but they are not orthogonal. You can take the dot product and see that it's not equal to 0. I want to form an orthogonal basis. So I'm going to follow this Gram-Schmidt process. I'm going to let the first vector be V1, just because it's convenient. Now I'm going to project V2 onto V1. So I'm going to take a flashlight and create this vector V2 hat. And so V2 hat is basically going to be V2 dotted with W1, which in my language is just the original vector, V1. Now is the key point. I'm going to define V2 perpendicular as V2 original minus this orthogonal projection, V2 hat, It'll be V2 subtract V2 W1, W1 dotted with W1. And that will be my second orthogonal vector. So I'm going to define W2 this to be that vector. So let's put some numbers in, okay? So we have V1 is 0, 2, which is the same as W1. So W1 dotted with itself is going to give me 4. V2 was the vector 1, 1. So V2 dotted with W1 is going to give me 2. So that means W2 is going to be V2 subtract 1/2 of W1. And in my case, that's going to be 1, 1 subtract 0, 1. So this is just going to give me, no surprise, the vector 1, 0. So I have now an orthogonal basis for R2. I'm going to call this basis W1, W2. It's going to be made up of two vectors, 0, 2, 1, 0. You can clearly see that when you take the dot product of those two, you're going to get 0. They're orthogonal. Now, the real key to going forward is that once we have an orthogonal basis, we would love to find something called an orthonormal basis. Now, an orthonormal basis basically says take the length of each one of these vectors and then scale your vectors so that they all have a unit length. Well, in my particular case here, W1 is not unit length, but W2 is. So the orthonormal basis we're going to call U1 and U2 for U for unit vector. That's an easy way to remember it. It'll be 1/2 of W1, W2, because W2 is already unit length. And no surprise, you're going to get 0, 1, 1, 0. Orthonormal bases are great. They have a lot of useful properties, as you're going to see going forward. But this is the first step here. The Gram-Schmidt process allows us to create an orthogonal basis for a subspace just by using projections. Now, I've only talked about projections in R2, but it's possible to go forward from there.